my dear students. So today we are going to have the topic hydrostatic force on plane surfaces. So in this topic, let us remember that whenever a plane surface is submerged into a liquid, there will be a force, and that force is expressed in P is equal to gamma H bar A. So P here is the total hydrostatic pressure or force on a plane area subjected to liquid. So the unit here is in kilonewton, while that of H bar is the vertical distance of the center of gravity below the liquid surface, and that shall be denoted by meter. A here is the cross-sectional area of the plane surface in square meter. Now, if we have here a liquid surface and a plane surface underneath or submerged into that liquid, of course, this shall have its center of gravity. So in this case, it is rectangular. So therefore, the center of gravity is simply located at the half of its height. So in here, from that center of gravity up to the liquid surface, this is what we call H bar. And then from the center of gravity down below the center of gravity, there will be the hydrostatic force, which is denoted by our P. Now, that distance is actually the value of E. Now, E can be computed by the formula I bar all over AY bar. So, the purpose of E here is to locate the hydrostatic force from the center of gravity, wherein I bar here is the centroidal moment of inertia in meters raised to 4, and then Y bar here is the distance of the center of gravity below the liquid surface along the body. So this is also in meters. Notice that we have here a common statement or definition of the H bar and Y bar, wherein it is the distance of the center of gravity below the liquid surface. So the main difference of this one is that H bar here refers to that vertical distance, while that of Y bar, it is along the body. So we can appreciate this difference if we have an inclined plane submerged into the liquid. So if this will be our liquid surface, and then an inclined rectangle is submerged into this surface, say this is a rectangular surface, just the same, it would have a center of gravity. Say this is the center of gravity, CG, and then from that CG up to the liquid surface vertically, this is H bar. So therefore, the distance of the center of gravity up to the liquid surface on vertical, that is H bar. So what is the difference on Y bar? Y bar here is to project this line up to our liquid surface. So therefore, this distance is our Y bar. So the difference is that the H bar is vertical and Y bar is inclined along the body. Whenever your plane is inclined, that is submerged also in the liquid surface. So in this case, our plane surface is on the vertical, so therefore h bar will still be vertical. And if we project the center of gravity up to the liquid surface along the body, so the body is vertical, so therefore h bar here is also equal to y bar. Now, just the same, from the center of gravity, we'll just have to measure a dimension E to locate our hydrostatic force. Say that would be our hydrostatic force. Notice that hydrostatic force is always perpendicular to the plane surface. And by the way, this location from the center of gravity up to the location of our hydrostatic force is denoted by Cp, or the center of pressure. So that is Cp. So therefore, the distance along the body from the water surface up to this center of pressure is denoted by Ycp. If we look at the dimension, Ycp is just simply equal to y bar plus E. So in this type of problems, we need to recall the centroid formulas as well as the centroidal moment of inertia formulas. Now for a rectangle, the center of gravity is half of the dimension. So if this has a dimension of b times h, its y bar, so y bar is here, referred from the base, is simply h all over 2. And for its centroidal moment of inertia, say if this is our centroid, so it is on I bar x, so therefore the centroidal of inertia on the x-axis of this rectangle is given by the formula bh cubed all over 12. So for a triangle of base and height, the centroid is located y bar from the base, say that is our y bar, or the centroid distance from the base is equal to h over 3. And the centroidal moment of inertia, I bar x, is bh cubed all over 36. Now for a circle having a radius r, say this is our y bar. So y bar is just simply equal to the radius referred from the base or on top of this circle. And for its moment of inertia, centroidal, say that is I bar x, we have pi over 4 times r raised to 4. For semicircle having a radius r, the center of gravity is just on top the point of origin, say that is y bar. So the formula for y bar is 4r all over 3 pi, while that centroidal moment of inertia, say I bar x, that is equal to 0.11 times r raised to 4. So these are the basic shapes that for the meantime we're going to deal with. We have a common shapes like rectangle, triangle, circle, and semicircle. So we just take note of the location of the centroid as well as the formula for the centroidal moment of inertia. We now go to examples. Say this problem, the figure shows a vertical rectangular gate AB on the upstream face of a dam. It is 1 meter by 2 meter in dimensions and weighs 800 Newton. If the upper edge of the gate is 4 meters below the water surface and the coefficient of friction F between the guides and the gate is 0.4, determine the minimum vertical force to open it. So here's the figure. Say we have here one face, or the upstream face of the dam, this one. So we have here the dam wall, and then of course a gate here. So between this gate there will be a guide here that would hold this enclosure of this opening. So we need to apply a vertical force to open it. See, that will be our vertical force. And the dimension of this vertical gate is 1/2 meters. So this will be our center of gravity, and that will be our center of pressure. So on that center of pressure lies the hydrostatic force P. So the dimension of this P from that center of gravity is dimension E. Of course, we also consider the weight of this gate equivalent to 800 newtons. See, there shall be 800 newton that is concentrated along the center of gravity. And then from that, of course, if we're going to have here a frictional force or a force to lift this gate, there will be a contact between the face and the guides of the gate. Hence, there will be a frictional force in here. So the frictional force is given by F sub F. So to have our free body diagram, let us consider here the gate, okay, and then from this gate we will have this center of gravity, and then below that will be the hydrostatic pressure P, and then we have here the weight of the gate, and then the force required to open the gate, and here the frictional force F sub F. And then from that we know that F sub F is mu times the normal force. So to get the value of the normal force, of course we know that the normal force is the perpendicular force here. Say this is the normal force. So what we do is to apply our equilibrium equations to come up with the frictional force, knowing P, and then the frictional force will be paired into summation forces vertical with together with that of the F force and W. But before that, we need to calculate the value of P. Now the value of P is equal to gamma H bar A. So we need here the value of H bar. So we refer H bar from the center of gravity up to the liquid surface. Say I'm going to label this as H bar. So H bar here is this one from the centroid up to this point, that is 1 meter, because half of the dimension of 2 plus 4. So therefore H bar will be equal to 5 meters. So going back to our formula, therefore the hydrostatic force is equal to the gamma involved here is a liquid water. So gamma of water is 9.81 kilonewton per cubic meter, with H bar equal to 5 meter, while that of the area is 1/2 meters. So if we investigate the units here, we have gamma to be equal to kilonewton per cubic meter, H bar is in meter, while that of area is in square meter. Therefore, those meter unit will be cancelled and P will be in terms of kilonewton. So that is equal to 98.1 kilonewton. So we also express W in terms of kilonewton because W here is in terms of newton. So we just divide that by 1000 to make it in kilonewton. So next step here, since we obtained the value of P here, we can now proceed in calculating the frictional force through the normal force. And the normal force by summation forces horizontal is equal to 0. We have the hydrostatic force should equate to the normal force. Hence, the normal force would be equal to 98.1 kilonewton. So knowing our normal force, we can now compute the frictional force. Hence, frictional force can be connected to the unknown force as well as the weight by summation forces vertical is equal to 0. First, we have going upwards F less going downwards frictional force less the weight of the gate, and those will be equated to 0. So next, F here is unknown. The frictional force is mu times the normal force minus the weight, that is equal to 0.8. So this is going downwards, negative 0.8 kilonewton. And then that closes to 0. So further, we substitute values. We have the coefficient of friction equal to 0.4 times the calculated normal force 98.1 minus 0.8 is equal to 0. Solving now for F, we have 40.04 kilonewtons. So that is about this problem. So the basics will come from your equilibrium equation and the free body diagram. So what is added here in fluid mechanics is the calculation of the hydrostatic force P. So if the gate of the first problem is hinged at its upper edge, determine the minimum horizontal force applied at the midpoint of the lower edge to open the gate. So if this will be our liquid surface and this is the upstream face of the dam, and then here is the gate on problem number 1. So instead of this gate to be on the guide, it will be hinged at that point. So therefore, we cannot open this simply by a vertical force, but rather a horizontal force acting on the midpoint of this lower edge. So if this is the force, say I will label this as H. Of course, we still have the hydrostatic force here, that is P, that is located E dimension from our center of gravity. So this time there will be no friction but a hinging action on the hinge support. Again, considering the free body diagram, we have the value of P equivalent to 98.1 kilonewton, and then the required horizontal force here, say just the same. From the centroid, there will be a concentration of the weight equivalent to 0.8 kilonewton. And for a hinge support, there should be a vertical and horizontal reactions acting on the hinge support. Say, if I'm going to name this as point A, there will be RAY and RAX. Nevertheless, if this is A, we can simply take moments at that A is equal to 0. We will have a certain distance, okay, distances to be considered here. Say the distance of H from A is equal to 2 meters, while that of the distance of the center of pressure up to this point will be equal to this E value plus 1 meter. So therefore, we can now perform this equation. Taking moments at A, we have 98.1, that is counterclockwise, negative 98.1 times 1 plus E plus the required horizontal force times 2 meters is equal to 0. So we need to compute for E. Now E will be equal to I bar all over AY bar. Hence E here is equal to VH cube all over 12 for a rectangle divided by base times height, the area, times Y bar. Substituting the values, we have E is equal to, the base is 1, height is 2, that is cube, divided by 12 all over 1 by 2 times Y bar, and Y bar happens to be equal to H bar also. So the calculated H bar a while ago is equal to 5 meter. So that is measuring the center of gravity vertically up to the liquid surface. So this is 5 meter. So with that, we can compute for value of E. So E here would be equal to 0.07. We just simply copy this equation and replace E equal to 0.07. So manipulation of equation and solving for the value of H would be equal to 52.48 kilonewton. So this will be the answer to this problem, or the required horizontal force to open the gate when it is hinged at the upper portion of the gate. Moving on to the next problem, we have the free surface of oil S is equal to 0.8 is subjected to a pressure of 7 kilopascal. Determine the magnitude and location of the total force on the 4 meter diameter circular gate as shown. So we can see here in the figure that we have an inclined gate that is in circular form. So this is 4 meter diameter, so therefore there will be a radius of 2 meters here, and then it is hinged at A. So this is actually gate AB, and from A it is 5 meters from the liquid surface. So in this case, we have here a surcharge at the liquid surface itself. So with that, we cannot assume that the value of the liquid surface will be 0. So therefore, there will be a corresponding head of this due to this 7 kilopascal, equivalent to the head of oil. So I'm going to label this yellow line as imaginary oil surface. So we need to establish this imaginary surface to accommodate the head equivalent to 7 kilopascal in terms of oil, because we cannot use this line as our reference for our H bar. So that is our first step. So let me denote that by HO as the head of oil due to 7 kilopascal. Now we use this formula, P is equal to gamma H in terms of oil. We substitute 7 for that pressure, and the gamma of oil is specific gravity 0.8 times specific gravity of water 9.81. So we're looking at HO Hence, HO can be computed as 0.9 meters. So we can place it here. So therefore, we can now compute for our H bar. So H bar will be reference from the center of gravity up to the liquid surface. Say this is the center of gravity. So we will use the imaginary oil surface instead of the original liquid surface because we have an equivalent head of 7 kilopascal. Now this shall be the total H bar. So the total H bar is 0.9 plus 5 plus this dimension. So I'm going to denote this by Z for a while. So Z is part of this right triangle here. Say this is Z. This is 45 degrees and that is 2 meters. So writing an equation from this right triangle, we can relate Z to that of 2 meters by function of cosine. Say cosine 45, sorry. So Z is opposite actually, so therefore we can use sine function, sine 45 degrees is equal to opposite Z all over hypotenuse 2. So therefore, Z is equal to 2 sine of 45 degrees. And as for our H bar will be equal to, we have 0.9 plus 5 plus Z, which is 2 sine of 45 degrees. So therefore, H bar will be equal to 7.31 meter. So our concern here actually is the magnitude and the location of the total force. So therefore, we'll just have to consider our free body diagram here. Say from the center of gravity, we'll be having the total force here below the center of gravity. And this is concentrated on the center of pressure just below the center of gravity by a distance E. So let us first solve the first unknown, say letter A, that P is equal to gamma H bar A. Gamma is 0.8 times 9.81 for oil, the 7.31 meter H bar, and the area of the circle pi over 4 times 4 raised to 2. Hence, we can solve for P equal to 721.33 kilonewton. So this is the magnitude of the force on that gate. So next unknown, say letter B, what is the location of this P up to the liquid surface? So as our reference and was discussed beforehand, we are referring to YCP. So at this juncture, let us focus ourselves on the center of pressure up to the imaginary liquid surface here. So from that, from CP, we project this along the body up to the imaginary liquid surface parallel to the body. And then from its intersection, so this is our dimension here. This is YCP. And YCP, from this point up to that, this is our Y bar. So therefore, YCP is equal to Y bar plus E. Now we can relate to Y bar and H bar because if you observe, Y bar is just the hypotenuse of this H bar given the angle 45 degrees. So looking at the triangle that is inclined along the horizontal line with 45 degrees, this is y bar and h bar. So again, relating h bar to y bar, we can use sine function that sine 45 degrees is equal to h bar all over y bar. And knowing h bar to be equal to 7.31, we can now compute for y bar. And that y bar is equal to 7.31 all over sine 45 degrees. So therefore, y bar is equal to 10.34 meters. So we are now done with y bar. So let us have the value for E. Now E is given by the formula I bar all over AY bar. For circular I bar, we have pi all over 4 times r raised to 4. And the area is pi r squared times y bar. So we substitute the given pi over 4 times 2 raised to 4 divided by pi 2 raised to 2 times the computed y bar 10.34. So that would yield to 0.096, or we can round that to 0.1 meter. So therefore, we are done with this one. So we can now compute for the unknown or the location of the center of pressure up to the liquid surface. That is 10.34 plus 0.1. We can have 10.44 meters. So this is the location of the force on this 4-meter diameter circular gate as shown. So moving on to the next problem. If a triangle of height D and base B is vertical and submerged in a liquid with its vertex at the liquid surface, compute the depth to its center of pressure. So we draw the figure according to the problem. So this is base B and this is height H. So the submerged in a liquid is that the vertex is just right at the top of the liquid surface. Say that will be our liquid surface. So our task is to compute the depth to its center of pressure. So now the center of pressure is just below the center of gravity. So this is the center of pressure. So our task is to determine this H up to the center of pressure. We know that the distance between the CG and the CP is E, and the center of gravity up to the liquid surface is H bar. So H bar will be added to E to come up with HCP. Hence, H bar can be derived from the formula of the centroid. Recall that the center of gravity of a triangle referred from the base is 1/3 of the height. So therefore, the remaining top dimension is 2/3 of the height to complete the dimension H. So if that is so, H bar here will be equal to 2/3 of height. So we can just place that on that portion and then we proceed to E. And then again, that E is I bar all over AY bar. We expand the expression by having the formula of I bar of a triangle, that is BH cubed all over 36. And then the area is 1/2 base times height times Y bar, and Y bar here will just be equal to H bar since we have a vertical shape. So along the body, so Y bar is from the centroid up to the liquid surface along the body, and the body here is vertical. Hence, H bar will be just equal to Y bar equal to 2/3 of H. So we place it here and perform the operations. So we first simplify this expression. We have BH cubed all over 36. On the denominator, we can just cancel this and then multiply the numerator by the reciprocal of this one. So BH times H, that is BH squared, will be reciprocated and transferred to the denominator. So, and that would yield to BH squared. So 3 here will be transferred to the numerator. Okay. Hence we can cancel B, cancel one of the H, and then H will be left. We can also cancel 36 and 3, and 12 will be left here. So we can place the value of E, H over 12, and then add to this one 2/3 of H. That will be our HCP. Now HCP is just simply getting the LCD. We have 12 over 3, that is 4 times 2, we have 8H. 12 over 12, that is 1, times H, that is 1. So therefore, this is 1H, so therefore this is 9H all over 12. So 9 over 12 is actually 3 all over 4 times H. So this is the value of HCP in terms of H, or the location of the center of pressure or the force up to the liquid surface. So that's it for this problem. So next problem, an inclined circular gate with water on one side is shown. Determine resultant force acting on the gate and the location of the center of pressure. So first things first, we're going to label the figure with the center of gravity, and below that will be the center of pressure, and on the center of pressure we have the force concentrated perpendicular to the gate P, and the distance between CG and CP is denoted by E. So in getting H bar, we need to get this distance here. Say this is Z. So utilizing our triangle here, so the triangle is 60 degrees. This is Z, and the diameter of gate is 1. So therefore, this is the half of the diameter, that is 0.5. So we can relate Z and 0.5 by function of sine. We can say that sine 60 is equal to Z all over 0.5. So hence Z will be equal to 0.5 sine of 60 degrees. So by that, we can get the value of H bar. So H bar is equal to Z plus 1.5. We substitute the value of Z and then add it to 1.5. We'll have the value of H bar equal to 1.93 meters. And then from that, we can now deal with the first unknown, P, which is equal to gamma H bar A. P here is equal to 9.81 kilonewton per cubic meter. The computed H bar 1.93, and the area pi times 0.5 squared. Therefore, P will be equal to 14.89 kilonewton. So this is the first unknown. This is the magnitude of the resultant force acting on the gate. So the second unknown is the location of the center of pressure. Again, this refers to YCP. And YCP is equal to Y bar plus E. Again, we can relate to the triangle of Y bar and H bar. Now this slope is inclined with the horizontal at 60 degrees. So we draw a horizontal line here. Therefore, this is also 60 degrees. So we can use that in the triangle to relate H bar and Y bar. So this is H bar and this is Y bar, and this is 60 degrees. Hence, again, we can use sine function. Sine 60 is equal to h bar all over y bar. So therefore, y bar is equal to h bar, which is 1.93 all over sine of 60 degrees. So therefore, y bar will be equal to 2.23 meters. So moving on to this equation, we still need to solve for E. And E is given by this formula, E is equal to I bar all over AY bar. And for a circular section, the moment of inertia centroidal is pi over 4 r raised to 4. So our radius here is 0.5, that would be raised to 4. And then we have pi r squared for the area of this triangle of radius 0.5, and then the computed y bar is 2.23 meters. So therefore, E will be equal to 0.03 meters. So therefore, can just substitute what we have computed, 2.23 plus 0.03, we have YCP will be equal to 2.26 meters. So this is actually the location of the center of pressure of this circular gate, 1 meter in diameter. So that's it for this problem. So for the next problem, we have here an upstream portion of the dam or in. We have here the floor. We have here the flooring. And here we have a smooth wall. Now this gate AB is hinged at B so that the other end will be resting on this smooth wall at A. So given the dimension, vertical and horizontal dimension here, and having this head to be equal to 5.2 meters, we are going to compute the force on the gate due to seawater of unit weight 10 kilonewton per cubic meter. So therefore, gamma here is 10 kilonewton per cubic meter, and this gate is 1.2 meter wide. So another unknown is the reaction force exerted on the wall and the reaction at hinge B. So we take the free body diagram of this gate, and this gate is, if you can see in the problem, that is 1.2 meter wide. So we can place here the section 1.2 meter, and this is actually unknown. This is distance AB, and that distance AB is part or hypotenuse of these two legs, 2.2 and 2.92. So we can see that hypotenuse is AB is equal to 2.2 squared plus 2.92 squared. We can have this distance to be equal to 3.66 meters. This is 3.66 meters. So the purpose of getting this dimension is to get the area and the distance to be utilized in the computation of our E and H bar as well. So as usual, we name this to be the center of gravity, this one, center of gravity, and below that is the center of pressure. So on the center of pressure, we have the concentrated P here with the distance between center of pressure and the center of gravity E along the body. So say this is parallel distance E. So we illustrate here the liquid surface, So this is the liquid surface, and the distance of this, since this is 2.2 and that is 5.2, the remaining dimension of this one up to this point is 3 meters. So we label this as 3 meters. Okay. From that, we can determine the value of h bar if we could determine this dimension. Say this is z. So therefore, this composes of our h bar. Okay. So we first solve for z. So if we're going to delegate this as our theta, and this is our theta, we use the triangle theta with theta angle, and this is z, and this is 3.66 all over 2. Place it there, and then relate z and 3.66 by function of sine. So we got this to be sine theta is equal to z all over 3.66 all over 2. So therefore, by cross multiplication, that is 3.66 over 2 sine of theta. So this time we need to get theta. So we can relate theta with these two given by function of tangent. Tangent theta, opposite to theta is 2.2. Adjacent to theta is 2.92. So theta here will be equal to 37 degrees. So therefore, we have here sine of theta, or that is sine of 37 degrees. We now go back to h bar. H bar is equal to z plus 3. We substitute the value of z, and then we add that to 3. Therefore, h bar will be equal to 4.1 meters. So if we know h bar, we can now directly compute for y bar. So y bar, the relationship between y bar is just simply by sine of 37 degrees is equal to 4.1 all over y bar. So therefore, y bar is equal to 4.1 all over sine of 37 degrees. So we have y bar to be equal to 6.81 meter. So by the way, class, in dealing with this hydrostatic force on plane surfaces, it is inherent that we need to compute for h bar and y bar, so that can address all the formulas we need. Okay, so knowing h bar and y bar, we can proceed with the solution of P gamma h bar A. So P gamma here is, according to the problem, we have gamma of 10 kilonewton per cubic meter. So this is 10 times computed h bar is 4.1 times the area is 1.2 by 3.66. So therefore, P here will be equal to 176.65 kilonewton. So which is actually the first unknown, the force on the gate due to seawater of unit weight. And then the next unknown, the reaction force exerted on the wall. So for the reaction force, exerted on the wall after B, we'll just have to refer to this. Since this is hinge at B, there will be two reactions at B, say By and Bx, and this is the center of gravity, this is the center of pressure. We have here P, and then this is E. Okay, we need that one because consequently we'll be dealing with this distance. Say this is x distance. So we need x because if we are going to take moments at B, by the way, there are still reaction here since this is resting on this smooth wall. So therefore, the reaction is always perpendicular to the wall. So that is reaction at A. So in here, we have several forces here. Nevertheless, we just take moments at B and equate it to 0. So summation moments at B, we have here P clockwise times x, and then this is counterclockwise minus reaction at A times the distance is 2.2 meter, and that would be equal to 0. So in here, we know this one. We still have to compute for x, and we also wanted to get the smooth reaction at wall A. So the second unknown is the reaction force exerted on the wall. So as we can see here, this is the gate. We have here the P, say By and Bx, and the reaction at A. So to solve for the reaction at A, we need to take moments this. So we need to solve for x. Now x here is this distance, and this is the center of gravity. This is our E, and this dimension is 3.66 all over 2. So therefore, the sum of x and E will be equal to 3.66 all over 2. So we use the formula for E, I bar all over AY bar. Of course, we just write this one. Okay, next, just copy that. We have a rectangular one here. BH cube of over 12 centroidal moment of inertia of a rectangle all over the area BH times Y bar is equal to the right hand side of the equation. Now we simply substitute all of the base and the height there in the Y bar. Base here is 1.2. Height is 3.66 raised to 3. We have here 1.2 times 3.66 times the computed Y bar is this one, 6.81. Okay, so we manipulate the equation and get for x. Eventually, we have 1.67 meters. Okay, so knowing x, we can now go back to this. So the computed P is 176.65 times x, this one, 1.67 minus the unknown reaction is 2.2 is equal to 0. So solving for RA, we have 133.77 kilo newtons. Okay, finally, we look on the reaction at B. So the reaction at B, we need to get Bx and By. So from this FBD, so by FBD of AB, we'll just have to take summation forces along x equal to 0. So remember this angle to be equal to 37 degrees. So we have rightwards Bx minus leftwards Ra plus the component of P. So this is the component of P along x, and that will be the component of P along y. So how shall we determine those components? So recalling your knowledge in mechanics, say this is our inclined plane. Remember, this is 37 degrees. Okay. Now this P is perpendicular to your inclined heel. So the rule here is, if we have a perpendicular line inclined to a certain angle, say this is perpendicular, we just create a vertical line, and this will be also its angle. So in this case, we just create a vertical line, and this shall be also 37 degrees. Hence, this is Py, and this is Px. So if you notice, Px is opposite the angle, and Py is adjacent to the angle, while the hypotenuse should be P. So the hypotenuse here should be P. So therefore, think we need to fix our drawing here. This should be Px, and this is Py. So again, Px is opposite the angle, Py is adjacent to the angle. Okay. So what we did here in summation forces horizontal is the horizontal component of P that is going rightwards. So we denote that by positive, and this is Px. So no more force. So we have Vx rightwards, Px rightwards minus Ra leftwards. So this equates to 0. So unknown here is Vx. We know Ra. We have 133.77 plus Px is the component of x, that is P. We have opposite, we have use sine 37 degrees. So that is equal to 0. So we know P to be equal to 176.65. So therefore, computing our Bx shall be equal to 27.46 kilonewton. Okay, so we also need to determine By. So we can get that by this equilibrium equation along the vertical. We have, look at this figure, the vertical ones are only By and Py. Hence, we can say that By minus Py is equal to 0, or simply equal to By is equal to Py, and then By is the component of y along the vertical, component of P along the vertical. So that is P. So this is adjacent to your angle. We use cosine. Cosine 37 degrees. And knowing P to be equal to 176.65, we have By to be equal to 141.08 kilonewtons. So now that we have the two components of B, or the reaction at B, we can now have the reaction at B. And the reaction at B is equal to square root of Bx squared plus By squared. So substituting the values, we'll have the reaction at B equal to 143.73 kilonewton. So this will be the answer for letter C, or the reaction at B. Okay, so with that, thank you and good day everyone.